Yeah. Yeah. Why didn't you tell me earlier?
I just found it.
Okay, yes, it is. Oh my gosh, that's great. That's great. Well, I'm going to write this down since you won't be able to answer this. So I'm going to write this down. So I'm going to write this down. So this is quite important. In the sense that plotting a box, we have a master equation. And so these are the ones. Please go ahead and write this down in your notebook. This is absolutely the basic things. Master equation. So these are master equations which we'll absolutely use them for particle in a box, quantum well. In other words, if you forget anything, everything, these two equations you cannot forget, because this is essentially the starting point when you get it. Particle in a box, the master equation is this guy. Assign Ka equals 0. This is essentially the boundary. You notice that here is a particle in a box. Here's 0, here's A, and this is where this point, doesn't matter what kind of wave function you have, it's this point. So this is the master equation. And this master equation, you see Ka equals, so this has to be n pi. So there's no other choice you could make. It has to be n pi in order to match this boundary condition. For this purpose, you see, now K carries n is subscript A. And that's where the entire quantization things comes out. For the tunneling, we didn't have these kind of equations. There's no constraint. So that's why there's no master equation. For the quantum well case, and then we have eta, omega, and cosine eta. And we say plus minus in the front like this. So that's what we did, used. And I think some of you remember this equation. This is our master equation. Now, you probably didn't realize this is somehow these two equations, they're not related to each other, right? They're not related to each other. This is the cosine, this is sine. There's a pure difference between these two. But of course, you know, this is we choose the even solution. So this is the even solution. For the even solution, we have this guy. But if we have an odd solution, we will have plus minus omega sine eta for the odd solution. For the odd solution, we have a different function all going on here. So this is one of the very, very, very important lesson in the sense that if they are the even function, we have this. So these are the absolute best. If you forget anything, you should not forget about this. Now, how this equation, which is, let's call it equation 1 here, use better pens. So how we have equation 2 goes to equation, let's call it 0. How do we get 0? 2 goes to 0. And this is a very, very so, Aisha, how do we get from equation number 2 becomes equation 0? How do we do that? Go from here to there. Let me write this down explicitly. In other words, let's just choose one positive root. How do we get this equation to this equation? From that equation, how do we get this equation? Yes?
Eta equals n pi.
Eta. Well, it's actually, my idea is simpler than this. Can you think a real extreme simple? Alex, how do we get this equation from here to this equation? Extreme simple one. How do we get eta, this equation, to this equation? Extreme simple. Extreme simple. Don't think it too complicated. Extreme simple. I should have any idea. Let me give you a little hints. This is very important. Did you see this? Question is when eta divided by epsilon goes to 0. When and at what condition? At what condition this goes to 0? What happens to omega? Omega has to be small or large? Large, how large that is in order to get a 0? Infinity, exactly. Did you see? The particle box is a really infinite potential. Did you see here? Infinite potential. That's why this limits, when you take the limit W goes to infinite, you will end up with a particle box. This is the simplest, to my knowledge, explanation. Instead of show the students, yeah, mathematically you can take approximation x, y, z. This is the simplest you could be done, because there's no other tricks involved. So then when you do this, this is going to be 0 like this. So then you notice that this eta self must be looks like a Ka like this. So then you can determine this. That makes sense to you? So in other words, oh my gosh, Dr. Zhang is lying to you. We thought we have 2 problems. Actually, single problem. The particle box is just a limit of the quantum well state. When the quantum well 2 potential becomes larger. So when this goes to infinite, this also means V0 goes to infinite. So that's why when we start to write this book, we resist the idea was that choose this V0 goes to negative. Because it goes to negative now, if you take a limit, student will posit, okay, you got a negative infinity now. This is the positive infinity. So there's a conflict of concepts in the student brain. So that's why we want to make sure, take positive ones when you take the limit and just go back to this one. So that's why when we write our own program, our own codes, we write them out. Oh my gosh, that looks really sweet. It's really sweet. And this is the key essence of that. Okay. Let me see any questions we have. Okay, so now you see they relate to each other in this way. Okay, that's it. Folks, we have stopped using Zoom now, so we can start with the teaching. I'm going to end this now. And as I said in the beginning, our first exam will be on Monday, and a review on Friday. So I will return the homework to you by the end of today. So I will leave grade homework in your mailbox. And then also post the keys online, and you can look at my keys there. So make sure you do double check them. So some of these will be on our exam. And I also promise you will upload the videos for today and also review sessions. Make sure you do watch them online, so that way you will be able to refresh some of your idea. Okay, you're ready for the next chapter. Now, the reason when we start to write this book was that in Griffith's book, what I just told you, we covered 2 chapters. Remember, we covered 2 chapters now. In Griffith's book, this is the first chapter, covers 3 different topics. And when I was teaching that, students always baffled. In the sense that you cover so much material with the one single chapter. It's just a little bit overwhelming. Chapter 3, harmonic oscillator. And harmonic oscillator is one of very important topic. And I always think that a good teacher should do some research and on this particular topic, so otherwise you don't know what actually is used. The book never mentioned quite a lot of things, regular books. So I want to show why we discuss this. Of course, they have a lot of physical usage for this particular ones. One is, of course, explain black body radiation. And this is really crucially important. So we did not cover in the first chapter black body radiation is because this chapter is devoted for that. So we don't want to go over too much without student understand the underlying physics. Second part, which is more important, this allows us to treat a classical particle which we call the bosons. And this including the photons, which we'll talk about briefly. And that's why we can talk about photoelectric effect. So the photoelectric effect we've been able to explain. Now, unfortunately, probably do not have the time to cover all these topics in detail. So that's the photon itself, so light quantum. Second is the phonons. Phonon is just a quantization of the vibration itself. And I want to explain this to you because my PhD thesis on the vibration in carbon-60. So the vibration things is my business. So this is called a vibration. So nuclear vibrations or any atom vibrations will be described by a phonon. You know, the quantization, and that's called a phonon. The quantum of the vibration is called a phonon. The light itself quantized is called a photon. So they are related to each other. These are called the bosons. And that's the vibration. The third one, which you do need to know a little bit chemistry, because my research is borderline between chemistry and physics. That's why I know a whole lot more. The third one, which is much more interesting, and this is so-called coherent control of molecular dynamics. So all the chemical reactions, including FM2 magnetism, FM2 chemistry, all relate to these coherent controls. You could have a molecular dynamics or many of these dynamics. This part, you can use a laser to control the entire things. You can control laser chemical reactions, and these are all utilized. A lot of this. So again, even though we just call it harmonic oscillators, but actually the cover topics a lot. We have a bosons, we have coherent control, so this is essentially, I cannot even touch that. It's just too much things which is utilized. In chemistry and in normally quantum chemistry, the people can stop over here to discuss their chemical reactions, like for instance vibrations. And for instance, in my research topic is C60, we have 170 modes. Vibrational modes. So 170 vibration modes. Some modes are like these, some are like these, and these are called pitching modes. It's enormous amount of this things is happening. So let's just give you a real short overview, and I don't want to overwhelm you. In other words, there are a lot of applications if we want to dig into that. Now we want to come back to the business. First one, we will talk about two things. We'll talk about operators. Second topic is Heisenberg uncertainty principle. And we will discuss these two topics intensively, because they are extremely important, and it's also very have a very many applications in these cases. So we are going to talk about operators and for these parts. And I want you, this section is a little bit more mathematical than you normally have. I put off for a long time, and so because some books that jumps into the operators immediately. So first, we're going to talk about the properties of operators. We already know some operators, like for instance the position operator, and the position representation is just x. That's the position operator we used. If we have a momentum operator in position representation, there will be something like these are called operators. And the thing that we are going to learn, we're going to learn the operators systematically. So we're going to represent in the generic situation. Suppose I have operator A like this. So we use hat on the top. We can add these two operators, another B, like this. We can add them up if we want. For instance, we put a classical number, let's call it C1, plus the C2. C1, C2 are classical number, which is not operators. So we always say classical numbers. It's just a number. It could be a function though, but it's not operator. So operator, we have hat on the top. If we combine this, these two A and B, and this will be, let's call it operator C hat, capital letter C hat. So in other words, this is called association and subtraction, addition. These are also called operator related to each other. So if you have two operators, add them up, it's also a good operator. You can also multiply these operators, but multiplication is a little bit complicated, so I'm going to show you over here. And the operator, usually it's going to be very complicated. It's because operators are matrices. So let me show you this way. If we have two operators, as I just wrote, A and B. So this is the A and B. Let's say A multiplied by B. So these operators are side by side like this. Now, so which means this is called multiplications. If I swap the order of these two operators, like B and A, normally these two are not equal to each other. Normally they are not equal to each other. In other words, these two normally not equal to each other. I could also do the divisions, like A operator divided by B operator, like this. And this is also called a division. But in quantum mechanics, if we write an operator like this, people used to say, well, it's better don't write this shape instead of just writing A hat B A minus 1. But to my knowledge, this is actually a much better way to write that down. This is because you see, you will have A in the front instead of B in the front, because this will be very different if you write on B minus A like this. So this will be very different. You know, this notation with the fractions and common fractions is a little more confusing because A over B, which one is the first? Right? Which one apply first? You have to tell me. But this is much clearer. Now, okay, if I have a function, let's say f here, f there, so I know, okay, so the b minus 1 is applied on the f first, followed by a. But here, if you look like that, nobody knows which one is actually applied first. So that's why in quantum mechanics, people try to avoid use these notation instead of this notation like that. Okay. Any questions so far? So far, so good. All right. So now, so usually, did you see I have AB not equals BA? And then you may wonder, but how large this is? In other words, they are different, but they have different by what? We don't know. We simply don't know. So then if this is something we don't know, we use a notation to represent something we don't know it. This is denoted by square brackets. Did you see I have A in the front? I will put A in the front. And comma and B, like this. And this bracket is called square brackets. This is square brackets. And these are called square brackets. And you may wonder, Dr. Zhang, can we use these brackets, curve brackets, or not? The answer is yes, but they mean differently. For instance, if I use the curve brackets like this, if I use curve brackets like these, and this just equals square brackets, watch carefully, I have a subscript plus sign. In other words, if I have curve brackets, this will be A, B plus B, A, like this. So that's why in quantum mechanics, the code with the square brackets versus curly brackets, you have to ask. Otherwise, nobody will tell you what the actual that is. And these brackets is invented by Dirac himself. And Dirac himself was a very intelligent in the sense that how do you simplify the notation quickly so that you can transmit the message from one person to another person. Now, we invent this not just because they are interesting, but they are very useful. And I want to show you why they are useful here. These brackets, did you see I have a square brackets? These square brackets is typically for the bosons. For the bosons. Bosons are the photons, phonons. The bottom one here is for the fermions. Fermions is electrons, protons. So in other words, the bottom brackets, you're going to wait until we talk about electron spins in that case. We won't be able to use them immediately, because right now we're just talking about bosons. So you always see these square brackets are in this way. So far, everything is so abstract. Now, what we call these things, in other words, a square brackets, we don't want to call it bracket. So this entire things we call commutator. Commutators, in other words, A, B, this is the commutator. And then we call it commutators, and one commutator, second commutator. Now this particular bracket we call it anti-commutator. Because you see, we have a plus sign like this. For those of you who cannot wait until I tell you something, you can rush to the chapter 7. You will see these anti-commutators for the spring part immediately. But for the moment, we just stuck with the commutator, so that's the difference. And these are relations that we also call commutation relation. So you would ask, do we have a commutation relation between A and B, which we will write it down? Do we have a relation with this? If they do, but then what is a commutator? So that's usually the common language. All right. So in other words, you cannot have everything has a commutator. For instance, I would ask, does a time and let's say X has any commutation relation between these two? And the answer, there's no commutation relation between these two, so there's no commutator. So that's when we communicate with each other. And then it would say, do we have a commutator between X and X, PX? Yes, they have a commutation relation. So then we can find out what's the commutator that would be. So that's in the common language. So in other words, when you talk to someone who knows quantum mechanics, you have to use their language in order to communicate. Otherwise, it will become a bigger problem. So we won't be able to communicate easily. So that is the one which we want. All right, we are going to do a little bit in-class practice, how to deal with these commutators, because a little bit abstract for the moment, but it's kind of obvious. And I want to show you what this will look like. So far, we only have two operators, A and B. What happens if we have a commutator? Let's say we have an example. Folks, let's look at page 59, example 2. I'm not sure on the page, what page that is. Let me try to find that. 59, everybody go to 59. Page 59, it should be just below equation 3.1.4. So 3.1.4 equation. So that's the example 2. Just below that. Can you find it? It's called operator commutation. Did you see proof like this? Yeah. It has example 2 on page 59. For these you have physical books you can. I've been able to find it. Yeah. Should be example 2. It says operators. Go to equation 3.1.4. Equation 3.1.4. Go to equation 3.1.4. Oh, you still have one. Yeah. Are you been able to find it?
I think so.
Okay. Yeah, should be. Yeah, just go ahead and read that example here. Are you been able to finish? Okay. Finished? Let's wait. Any questions for this? Is student finished? You got it? Okay, very good. So that's the example 2. Okay, sounds good. Excellent. Anybody has any questions? Yes, question.
Could you show one of the expansions for like?
Oh,
the
sure.
First term on the right side for like ACB.
Okay.
So
So
I'm just confused on how that turns into those two terms.
okay, very good. Let me write this down. So you guys have no question to get this. Do you guys have any question on this? In other words, A, B, C equal this. Any question on this? There's no question about it. Now, next thing that we did was we plugged this one here. We moved this guy a little bit further down the road, and we minus A hat, C hat, and B hat. So minus this, and then plus the same terms. Of course, this is still valid, like this. So we just minus this one and plus that one. So they're exactly the same thing, right? And we have a one last term is over here. CABs. Tobin, are we good? So in other words, I plug these two terms, just cancel them out. I just plug these terms.
Yeah.
And this is this, and this is just that. And these in the middle, these two, basically I can cancel them out. Okay, so are we good? We can cancel middle term.
Because A and B are together, so they just split.
You mean middle term?
Yeah.
Middle term I invented. I didn't do anything. I just invented this term. I actually can add any term that I wanted. I could add minus D plus D. I have no trouble with it. I just can add anything. I can add because you add minus term, add term, so you can do whatever you want to do. So this term is basically arbitrary. So this order, I purposely add that such a way that I can pull out one of the, in this case, pull out A. That's the purpose. So this one here, I purposely added. And you may want to, how do you know what kind of term you're going to add this, right? In the beginning, I have no idea, just like D. How do we know that? Well, what we try to see is that we try to prove that relationship. Therefore, if you look at the proof, and if you read the problem, it says that prove A, B, C equals A, C, B, and plus A, B, C. So that's why the A must be in the front, and the second term, and the B should be in the back, like this. So now you can see, once I purposely add this term, tell me, are we good? Are we good on this? You know, which
I get what you're doing. I'm just struggling to follow.
Do you have any question from the first line to the second one?
No, I get that part.
So this is good. So in other words, anybody has any question from here to here? Everyone's good. Can I get thumb up, everybody? Okay, very good. Now next term, what I do the second here. So I will focus on this particular term first, and second work on it. Did you see these two both have A in the front? I can pull them out because each of these have common coefficient. So what I do the following. A, pull them out. B, C, C, B. These are just association, which means that you can put some of these operators in front, back, doesn't matter because you didn't change the order. So you pull this out. So you pull up A out and get a B, C minus CB. And for the next ones, I do the same, except this time pull out the B. So then A, C minus C, A. So you see, I pull out the B at the very end. So the next term, I pull out the B. So you see, first term, I have A in the front. These two common coefficient, I can pull out A. And now next two terms, I have a common B common out. I'll pull a B in the back. And you may wonder, can I pull out the two in the front? No, because normally these operators are not commutable. You cannot just swap them. No, you cannot. These are not numbers. So that's why I only can pull out the B. Can I pull out A? No, because here's A is not in the front, it's in the middle. Can I pull a C? No, you cannot do that, because C is in the middle. Here's in the front, but this is in the middle. So the only thing they can pull out is a B. So that's the key. Are we good? Yeah. So this is how the operator manipulates. In the sense that for the A, I pull out the A, for the B, I pull out the B. Are we good at this particular step? Are we good? Okay. Good. Toby, I will linger it up. Once you take this, I will show you, give you a practice. And once you practice, you will get more experience on it. So, but you have no question on this. Do you have any question from this step to this step?
Not there.
Okay. Now, once I'm done with this, B, C, C, B, this is just the same commutator which we have. In this case, A, B, B, A. So therefore, we have a B, C, like this. In other words, from here to there is which we use the definition of our commutator. That's what we did. We didn't do anything. In this case, my B here is A, my C here is a B, so that will be B and C like this. I didn't do anything. And the next term will be exactly the same. So I'm A hat, C hat, B, like this. So the next term you see here, A, C, C, B, so this will be A, C, and B, like what I did here. And this is the example I want to show you this way. So literally, this essentially what that means is that I can pull the A. You see here what I basically did. I pull this A out. So what I left over is going to be C. And then this is the first term. Second term, I pull the B out, CB, and then have a B. Essentially, that's how I remembered it. Did you see I have A in the front, pull it in the front. A in the back, pull it in the back. So that's what I did. So this will be exactly the same thing. This is how I remember them. That's how do I get these results. So that's the difference. Let me give you a practice problem. So this I practiced. I purposely prepared for this for the class. Okay, yes, here's the practice problem. See whether you understand this. This is a practice. Folks, let's practice this. I have A, B, C. Folks, I have A, B, C now. In other words, not A, B, C's. B in the back now. And how large this is going to be. I give you 5 minutes to work on these questions. Which step is it?
So we go from ABC to ACB.
This is a continuing line, I understand. Yeah. Okay.
But then when we jump down to factor out, like on the board, we went to A, BC minus CB. Here we go to BC minus AC.
No. I swap here. This term is this term. You see here. This term here. Oh, forgive me. This is the misprint. I didn't realize. Sorry, this is a misprint.
Oh, okay.
Oh, sorry. Toby, you pointed out. I didn't realize. It was a misprint.
I was trying to follow it.
I know. Well, you are good. Really good. Oh, my gosh. There is a misprint, folks. Forgive me. There is a misprint. There is a misprint.
Misprint.
There's a misprint. I will write this down. CB. In the second line in the book, there is a misprint. The misprint was that in the textbook, this is written as AC. This is written as AC. This is written as AC. Should be CB. Folks, could you make corrections? This term should be CB. This term should be CB. Yep. The book is incorrect. Should it be? Yeah, I need to write this down, folks. Just give me a second. You see, it's good that I use this book. Otherwise, it won't be able to correct. Page 59. Yeah. Page 59, the solution should be CB. I did not realize it should be CB. Now, to me, now you're good, right?
Yeah.
So that would be CB. Yeah, yes, yes. Did you see that? Did you see the arrow print? Should be this part of CB. Yes, exactly. Yeah, that should be, instead of AC, should be CB. Instead of AC, should be CB. Okay, got it? Where's your book? Oh, okay. Well, you let me know if you have troubles with this. All right. Okay, wonderful. Thank you so much, Tobin. So, folks, let's work on this. How about that? Let's take 5 minutes to work on this. Okay. Yeah. Yeah, let's work on this. Okay, let's work this out. Yeah, make sure you do it in class, work that out. Yeah, it's quite important. If you have questions, please let me know. Write them down in your notebook so that way I can check, see whether they get a correct answer. If you didn't, then take a look what you got. Finished? Okay, let me take a look what you got. I'm excited. All right. term that you added, it won't allow you to separate. Let me show you on what. So A, B, C, and I'm going to move this one a little bit over here. So it would be C, A like this. So now you see over here, if I, let's say minus A, C, B, suppose you add this. So then when you do this, this will, if you do like this, you have to add the same term like this. If you subtract this, you add the same term like this. So these two must cancel out. Otherwise, you cannot just arbitrarily plug it in. You won't be able to cancel. But in this case, when you add this term, it won't allow you to simplify further. Let me show you why. You see, this term, yes, you can pull out A and B, C. But this term cannot do anything with that. So you see, this term doesn't allow you to pull out another factor in the front. So you cannot pull out A because there's A in the back. You cannot pull a B because B in the front. So therefore, this term, you should not subtract this term. Instead, you should do like this. In other words, not subtract this, you minus, watch carefully. So in this case, it's not pull out of A. Instead of just write a B, A, C, like this. So then, minus this term, then you can see immediately, I can pull out C. The second term, B, A, C. You see, this has to be negative, this has to be positive, canceled out. The next term, actually you can see. Now the next term, I can pull out A. Did you see I can pull out A now? B, sorry, B and B now. This term, I can pull out C. So in other words, when we plug in something, we have to make sure, can you simplify them further? So this is the only way you actually can simplify this. I'm not sure whether you guys got it. Tell me, did you get it? The message. In other words, this is the only term you cannot plug it in. This is the only term you cannot plug it in. If you plug in something else, you cannot simplify them further. So that's the key. Okay. And this is the way you just practice. If you try to insert these two terms, then you cannot simplify further. The first term, yes, you can pull out A, but the second term, you cannot pull out anything. So that's why the one that we plug it in, these two terms like that, it won't work. It only works if you plug the bottom part. You know, it only works if you plug this part in. This is the only case it will work. So that's why the quantum is very something stuck there. You have to stuck with those ones, otherwise nothing will work. Does it make sense to you? So this is the one and which we use. Now let me just finish the entire thing. So therefore you have a B, C like this, and the last term. So now, can I erase this bottom part? Can I erase the bottom part? I'm going to erase the bottom part. So now we can see it clearly. So now, I'm going to combine these two terms together. When I combine these two terms together, so I can pull out C now. Because C is the same, all in the back side. So I can have A, B, pull out C now, and have a B, A, and I pull out C. So that's my first two terms. And next two terms, I use the double arrows, represent these double arrows. And these two terms, I can pull out the B. So this B can be pulled out. B can be pulled out. I have A, C hat, A hat, like this. Now I can simplify further because A, B, B, A is just the commutator A and B, C hat, B hat, and A hat and C hat, like this. And that's the one that we will have. Okay. So that's what commutator is. It's a little bit trickier. You cannot just plug in something and get a result. And we will assign some homework for the next week, so you guys will be practice a little more on this. Sounds good? Okay. And I do not expect you will understand immediately, because when I was learning quantum mechanics for this part, no, the professor finished it, and as I go back home and I think about, oh, that's why I test all these possible cases like Those ones, it won't work because you only have first term, you can simplify, but not the second term, so it's stuck there. And we designed a couple of them. You can practice them, but I will assign in class as well for the next week. Sounds good? Okay. All right, once again, the exam, sample exam already posted. And for the constructor questions, I won't review them because these will be all in my notes, and I will try to upload all of them to the my OneDrive folder, and you can click that. And the video will be posted, almost the entire video will be posted. You just watch these videos will be for you guys. All right, that's it. That's it. And I promise you I will grade the homework after this, immediately actually. So, but I hopefully won't take you too long to grade them. But it could. It could. All right, so I'm going to stop the recording. So that will be it.